Hi everyone, I am Bireshwar Roy. I am currently pursuing my fourth year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this video, I will be discussing all the questions from the topic solid state physics came in the exam GATE Physics 2021. This question was asked in the GATE Physics paper 2021. This is a MCQ type 1 mark question, and this question is from the topic solid state physics, specifically from the chapter dielectric properties of material. The question is, choose the graph that best describes the variation of dielectric constant epsilon r with temperature capital T in a ferroelectric material where Tc is the Curie temperature. So there are four graphs given. We have to identify the actual graph which describes the variation of dielectric constant of the ferroelectric material. So let us see the solution to get the proper graph for the ferroelectric material. Ferroelectricity is the state of spontaneous polarization in a material, that is, the polarization of the material in the absence of an electric field. So this ferroelectricity is analogous to ferromagnetic property of material or ferromagnetism, which represents the state of spontaneous magnetization in that ferromagnetic material. Now, the materials which exhibits ferroelectricity are known as ferroelectric materials or ferroelectric crystals. The examples of such materials are BaTiO3, that is barium titanate, K(PO4), that is potassium dihydrogen phosphate. There are some other materials also, etc. Now, the dielectric constant of ferroelectric materials varies as the temperature increases or decreases. The variation of dielectric constant with respect to the variation of temperature is described in the Curie law. So, this Curie law depicts that the ferroelectricity disappears above a certain critical temperature known as transition temperature or the Curie temperature or Curie point, that is Tc. So mathematically, the Curie law says the dielectric constant depends on the temperature in this way, that is A by mod of T minus Tc, where A is constant, T is absolute temperature and Tc is the Curie temperature, which is also known as phase transition temperature. So this temperature of the ferroelectric material, if it is less than Tc, then it is in ferroelectric state, and if it is greater than Tc, then it is in paraelectric state. So in the paraelectric state, as the temperature increases, the dielectric constant starts to decrease. Now we have already seen from the Curie law, the dielectric constant as a function of T for the ferroelectric materials is given by this. So here, if T greater than Tc, then the material is in paraelectric state, and if it is T less than Tc, then the material is in ferroelectric state. And T is equal to Tc is the phase transition from ferroelectric to paraelectric state. Now, if we plot this function, this epsilon r as a function of t, then first it will increase up to Tc. Then, if the temperature is greater than Tc, then it starts to decrease. So, our option A, the plot given in the option A, is the correct answer for this question. So, according to our solution, we found that the option A, that is the first graph, describes the variation of the dielectric constant epsilon r properly with temperature in a ferroelectric material, where Tc is the Curie temperature. So Tc is actually the phase transition temperature from ferroelectric phase to paraelectric phase. This question was asked in the GATE Physics paper 2021. This is a MCQ type 1 mark question, and the question was asked from the topic solid state physics. The question is, as shown in the figure, X-ray diffraction pattern is obtained from a diatomic chain of atoms P and Q. The diffraction condition is given by A cos theta equals to n lambda, where n is the order of the diffraction peak Here A is the lattice constant and lambda is the wavelength of the X-rays. Assume that atomic form factors and resolution of the instrument do not depend on theta. Then the intensity of the diffraction peaks is option A, lower for even values of n when compared to odd values of n, option B, lower for odd values of n when compared to even values of n, option C, 0 for odd values of n, and the last option, option D, 0 for even values of n. So we have to choose the correct option. In order to solve this question, what we have to find is that the resultant scattered X-ray intensity on a particular plane as a function of the order of the diffraction peak. Let us see the solution. According to the question, we have to deal with this diatomic chain of atoms P and Q, where the distance between consecutive atoms P and Q is A by 2 and the lattice constant is A. If we look into this one-dimensional crystal structure carefully, then we can find that unit cell of this crystal structure will be this. This unit cell consists of two bases, that is P and Q. From now onwards, we will use only this unit cell for our future calculations. The diffraction condition is given by A cos theta equals to n lambda. Now we will multiply 2 pi by lambda on the both sides. So we will get 2 pi by lambda into A cos theta equals to 2 pi n. Now 2 pi by lambda is k naught, which is basically magnitude of incident X-ray wave vector. Our diffraction condition then becomes k naught A cos theta equals to 2 pi n. One more thing we have to consider, that is atomic form factor of the atoms P and Q. Now the atomic form factor or the atomic scattering factor is defined as amplitude of scattered X-ray radiation from an atom divided by amplitude of scattered X-ray radiation from an electron in that atom. So Fp is the atomic form factor of the atom P and Fq is the atomic form factor of the atom Q. Now consider this schematic diagram. So the X-ray radiation will incident on the atoms P and Q. The electric field of the incident radiation is given by E naught vector e to the power I k naught x, which is basically a plane wave equation. And then the X-ray will get scattered from P and Q. Here we will be considering only the scattering at an angle theta. Also we will assume a plane AB which is perpendicular to the scattered X-ray radiation from P and Q. After scattering from P atom, the X-ray beam will gain some extra phase due to the path length PC on the plane AB. Now the PCQ triangle is a right angle triangle. So PC is given by PQ times cos theta. Hence PC will be A cos theta by 2. So the extra phase gained by the scattered X-ray radiation from P atom will be k naught A cos theta by 2. Q atom is placed on the plane AB. So the scattered radiation will not effectively gain any phase on the plane AB. So resultant electric field of scattered X-ray radiation on the plane AB is given by Fp E naught vector e to the power I k naught x plus k naught A cos theta by 2 plus Fq E naught vector e to the power I k naught x. So first term is due to the X scattering from P atom and second term is due to the X scattering from Q atom. If we take E naught vector e to the power I k naught x as common, then we will get this. Now we will apply the diffraction condition, that is k naught A cos theta equals to 2 pi n. Then we will get ER vector equals to E naught vector e to the power I k naught x multiplied by Fp e to the power I n pi plus Fq. Therefore, the resultant intensity on the plane AB is given by IR proportional to electric field multiplied with its complex conjugate. So, IR proportional to E naught square into Fp e to the power minus n pi plus Fq multiplied with Fp e to the power in pi plus Fq. If we just multiply these two terms, then we will get E naught square multiplied with Fp square plus Fp Fq e to the power in pi plus e to the power minus in pi plus Fq square. Now from the complex number theory, we know e to the power I theta plus e to the power minus I theta equals to 2 cos theta. Applying that formula, we will get the resultant intensity is proportional to E naught square multiplied with Fp square plus Fq square plus 2 Fp Fq cos n pi. Hence, we found the resultant intensity as a function of the order of diffraction. Here, two possibilities will come. One is for odd values of n and other one is for even values of n. For the first case, n equals to odd, this cos n pi equals to minus 1. Effectively, we will get IR proportional to E naught square multiplied with Fp square plus Fq square minus 2 Fp Fq. So for n is equal to odd, it will be E naught square multiplied with Fp minus Fq whole square. Similarly, for n is equal to even value, cos n pi will be plus 1. Hence, we will get the resultant intensity for n is equal to even proportional to E naught square multiplied with Fp plus Fq whole square. Clearly, it has been seen that this resultant intensity for n is equal to odd less than the resultant intensity for n is equal to even. So, among the four options, the option B is correct answer. So, the option B is lower for odd values of n when compared to the even values of n. This is the correct answer for this question. This question is from the GATE Physics paper 2021. There is a MCQ type question having 1 mark and the question was asked from the topic solid state physics. The question is choose the correct statement from the following. Option A, silicon is a direct bandgap semiconductor. Option B, conductivity of metals decreases with increasing temperature. Option C, conductivity of semiconductors decreases with increasing temperature. And the last option, option D, gallium arsenide is an indirect bandgap semiconductor. So here four options are given. We have to choose the correct statement among these. So we'll verify all the options one by one and we'll check which option is correct among these. Let us see the solution part now. The first option, option A, is false because silicon is an indirect bandgap semiconductor. Now this is a typical EK diagram of an indirect bandgap semiconductor. The band gap is defined as the difference between the energy at the conduction band edge and the energy at the valence band edge. Now, in order to have an electronic transition from valence band to conduction band, the electron has to gain the energy equals to band gap of this system, that is EC minus EV. But this is not only the case, because in order to have the transition, electron has to change its momentum to reach the conduction band edge. That is the momentum difference between this conduction band edge point and the valence band edge point. Now, this extra momentum to the electron is provided by the phonon, which is basically the quanta of the lattice vibration of this semiconductor. So, in the indirect semiconductor, the electron rising from valence band to conduction band will change its energy as well the momentum. The second option, option B, is true, which is conductivity of metals decreases with increasing temperature. From the root model, we know conductivity of a metal is given by N E squared tau by M, where N is the carrier number density, E is the electronic charge, tau is the relaxation time or mean collision time, and M is mass of electron. Now with change of temperature, the carrier number density n doesn't change much. Effectively, it will remain unchanged. But the collision time or relaxation time decreases with increasing temperature because this scattering probability between the electron and ion core increases. So your option B is correct. Now the option C is false because conductivity of semiconductors increases with increase in temperature. We know as the temperature increases, more and more electrons will be excited to conduction band from valence band, and it results in the number density of electrons and holes will increase in conduction band and valence band respectively. Hence, the conductivity of the semiconductor will increase as the temperature increases. Your option D is false because gallium arsenide is a direct bandgap semiconductor. If we see the EK diagram for the direct bandgap semiconductor, the edge of the conduction band and the edge of the valence band lies at the same K point. So, in order to have a transition, electronic transition from valence band to conduction band, the electron needs only the energy which is equal to the band gap of the semiconductor. Electron doesn't need any momentum change because the edge of the conduction band and the edge of the valence band lies at the same K point. So in direct bandgap semiconductor, the electron rising from valence band to conduction band will only change its energy. So we checked all the statements one by one thoroughly, and we found that only the options B, that is conductivity of metals decreases with increase in temperature, is the correct one for this question. This question was asked in the GATE Physics paper 2021. This is a multiple select question, that is MSQ, having 1 mark. The topic of the question is solid state physics. Specifically, this question was asked from the chapter Reciprocal Lattice. The question is, a two-dimensional square lattice has lattice constant small a. K represents the wave vector in reciprocal space. The coordinates kx, ky of reciprocal space where band gap or band gaps can occur, those are: option A is at 0, 0, that is at origin. Option B plus minus pi by a, plus minus pi by a. Option C plus minus pi by a, plus minus pi by 1.3a. And the last option, option D, plus minus pi by 3a, plus minus pi by e. So as this is a MSQ type question, so it is possible to have multiple options correct for this question. So let us see how to solve this problem. Before going to the main part of the solution, let us discuss very briefly about the Brillouin zone and how can we construct the Brillouin zone for a 2D square lattice having lattice constant small a. So what is Brillouin zone? Brillouin zone is the locus of all those k values or k points in the reciprocal space or k space of a crystal structure which are Bragg's reflected. So you can see here a schematic which basically describing the first and second Brillouin zone of a 2D square lattice having lattice constant small a. So let us understand how can we describe the first and second Brillouin zone for this from this schematic. So you can see here a square region which is shaded by the horizontal lines, and origin is at the middle of the square. So this square region is basically bounded by 4 straight lines. Those are kx equals to minus pi by a, kx equals to pi by a, ky equals to pi by a, and ky equals to minus pi by a. So this square region is the first Brillouin zone for the 2D square lattice in the K space, that is Kx, Ky plane. And these 4 sides which are basically the four state lines. These are the first Brillouin zone boundaries. So this is how we can describe the first Brillouin zone boundary for a 2D square lattice. Now what about the second Brillouin zone? So to construct the second Brillouin zone, basically we need these four state lines: kx minus ky equals to minus 2 pi by a, kx minus ky equals to 2 pi by a, kx plus ky equals to minus 2 pi by a, and kx plus ky equals to 2 pi by a. So these four lines, straight lines, will basically construct the second Brillouin zone for the 2D square lattice. So the area enclosed by these four lines, excluding this first Brillouin zone area, will give the second Brillouin zone. So basically these four region shaded with vertical lines will basically give the second Brillouin zone of the 2D square lattice, and the boundary lines are the second Brillouin zone boundaries. Now let us see how can we basically construct these Brillouin zone and Brillouin zone boundaries from the vector form of the Bragg's law. So let us see. In the previous slide, we have already seen the first and second Brillouin zone for the 2D square lattice having lattice constant small e. Now we'll understand how can we construct the Brillouin zones and Brillouin zone boundaries from the mathematical equation. For this, we need primitive translation vectors for the 2D square lattice. Those are a vector equals to a I cap, that is along x cap direction, and b vector equals to a j cap along y cap direction. The corresponding translation vectors in the reciprocal space, that is in the K space, will be a star vector equals to 2 pi by a along I cap direction, and b star vector equals to 2 pi by a along j cap direction. So by knowing these a star and b star vectors in the K space, we can construct the reciprocal lattice vector, that is g vector equals to 2 pi by a times h I cap plus k j cap, where h and k are the integers. And the wave vector in the K space, that is k vector, is basically kx I cap plus ky j cap. So the vector form of the Bragg's law is given by this equation. This equation is 2 times k vector dot product with g vector plus g square equals to 0. From the earlier slides, we have already seen this k vector is the wave vector in the kx ky plane. So this k vector will be kx I cap plus ky j cap, and g vector basically denotes the reciprocal lattice vector for the crystal structure, two-dimensional square lattice. So this g vector for the two-dimensional square lattice will be 2 pi by a times h I cap plus k j cap. Now we'll put all the expressions for the k vector and g vector in this equation. Then we'll get 4 pi by a times kx I cap plus ky j cap dot product with h I cap plus k j cap plus 4 pi square by a square times h square plus k square equals to 0. So this second term is coming for the g square term here, and this 2 times k dot g vector is giving this first term in this equation. Now we'll perform the dot product here. It will give the kx I cap dot product with h I cap will give the hkx, but this kx I cap dot product with kj cap here will give the 0 because I and j are the unit vectors orthogonal to each other. Similarly, ky j cap dot product with h I cap will give 0, but the ky j cap dot product with k j cap will give k ky. So after some rearrangements, we'll get this equation hkx plus kky equals to minus pi by a times a square plus k square. Here h and k are the integers. So what does this equation tells us? So this equation basically telling us about the location or locus of the k points which are Bragg reflected. Now h and k are the integers. So first we'll put h equals to plus minus 1 and k equals to 0. So this will basically lead to kx equals to plus minus pi by a and ky can be any arbitrary value. Similarly, we can put h equals to 0 here and k equals to plus minus 1. This will basically lead to ky equals to plus minus a and kx can be any arbitrary value. So from this combined of these conditions, we can get kx equals to plus minus pi by a and ky equals to plus minus pi by a. So these are basically constructing the boundaries for the first Brillouin zones. So these four lines will give the first Brillouin zone boundaries here. That we have already seen in the first schematic diagram. So till now we have already seen how can we construct the first Brillouin zone boundaries for the two-dimensional square lattice from the vector form of the Bragg's law. And those four lines are kx equals to plus minus pi by a and ky equals to plus minus pi by a. So these four lines are the boundaries for the first Brillouin zone that we have constructed mathematically already. Now we will consider the second possible integer values for the h and k. So those are h equals to plus minus 1 and k equals to plus minus 1. So if we put this h and k value in the equation of the locus of all k points, those are Bragg's reflected, then this will get another four lines which will basically give the boundaries for the second Brillouin zone in the 2D square lattice. So then we will get these four lines kx minus ky equals to minus 2 pi by a, kx minus ky equals to 2 pi by a, kx plus ky equals to minus 2 pi by a and kx plus ky equals to 2 pi by a. These four lines will basically construct the second Brillouin zone boundaries in the kx and ky plane. So now we have the idea how can we construct the Brillouin zones for the 2D square lattice and how does it look for the first Brillouin zone boundary and second Brillouin zone boundary. Now whenever an electron strikes the Brillouin zone boundaries, its group velocity, which is given by Vg equals to 1 by h cut del E del k, where E is the energy and k is the wave vector, that becomes 0 as at the Brillouin zone boundaries. What does it mean? It leads to basically the generation of energy band gap or energy gap at the Brillouin zone boundaries. Hence, all points lying on Brillouin zone boundaries will give rise to energy band gap in the crystal structure. Now, all the k points of first Brillouin zone boundary lies on the four lines. Those are kx equals to plus minus pi by a. These two lines are shown here, kx equals to minus pi by a here and kx equals to pi by a, and ky equals to plus minus pi by a. Those two lines are here, ky equals to pi by a and ky equals to minus pi by a. So these four lines will basically construct the boundary of the first Brillouin zone, and at all the points on this boundary we'll get the energy band gap. Now there are 4 points given in the options. First option was 0, 0, that is the origin. So the origin is not lying on the boundary, so it is not possible to have the energy band gap at the origin. So this option can be eliminated. Now for the other 3 options, so we will just discuss one by one. First, second option was plus minus pi by a, comma plus minus pi by a. So these are basically 4 points. These 4 points are here at the corner of the square. So these are lying on the boundary of the first Brillouin zone. So this is the possible answer 1. So then the third option, plus minus pi by a, comma plus minus pi by 1.3a, these points are lying somewhere like here, here, or here and here. So these 4 points will lie on the boundaries. So this is also possible answer. And for the last option D, plus minus pi by 3a comma plus minus pi by a, these 4 points will basically lie somewhere like here, here, or here, or here. So these 4 points will lie on the boundary of the first Boolean zone. So this is also the possible answer. So effectively we are getting option B, C and D are correct for this question. We have already discussed in the earlier slides about the Boolean zone. Then how to construct the Boolean zone for a two-dimensional square lattice that has lattice constant small a. Then we have discussed how the energy gap or band gap can arise at the zone boundary, that is at the boundary of first Boolean zone, second Boolean zone, or so on. And after that we solved this problem and we found that the option B, C and D, that is at plus minus pi by a comma plus minus pi by a, plus minus pi by a comma plus minus pi by 1.3a, and plus minus pi by 3a comma plus minus pi by a. So these three options B, C and D, at this point in K space the band gaps can occur. So these three options are the correct answer for this question. This question was asked in the GATE Physics paper 2021. This is a numerical answer type 1 marks question, and the topic of the question is solid state physics. Specifically it was asked from the chapter Semiconductor Physics. The question is, the donor concentration in a sample of N-type silicon is increased by a factor of 100. Assuming the sample to be non-degenerate, the shift in the Fermi level in millielectron volt at 300 Kelvin rounded off to the nearest integer is, so some information has been given, that is Kb times T equals to 25 millielectron volt at 300 Kelvin. So let us see the solution part now. We know in an intrinsic semiconductor, the electron density N in the conduction band and the hole density in valence band is equal, and that is denoted by Ni, where Ni is the intrinsic carrier density. Now, Fermi level for this type of intrinsic semiconductor is given by intrinsic Fermi level Ei equals to Ec plus Ev divided by 2 plus 3 by 4 kBt times ln of mp star by mn star, where Ec is the energy at the conduction bandage, Ev is the energy at the valence bandage, T is the absolute temperature of this semiconductor, mp star is the effective mass of the hole in the valence band, and mn star is the effective mass of the electrons in the conduction band. So from the diagram we can see the intrinsic Fermi level will lie in between the Ec and Ev energy level. If we perform external doping in intrinsic semiconductor, then it is known as doped semiconductor or extrinsic semiconductor. Depending on the type of impurity doped in the semiconductor, it is classified as two types. First one is N-type semiconductor and the second one is P-type semiconductor. In the N-type semiconductor, the doped impurity acts as donor of electrons in the conduction band. Hence, the electron density in the N-type semiconductor will be increased. But in P-type semiconductor, the doped impurity acts as acceptor of electrons from the valence band. So here, the hole density will be enhanced in P-type semiconductor. If we see the band diagram of N-type semiconductor, the donor energy level ED will lie above the intrinsic Fermi level EI. At 0 Kelvin temperature, all the donors are in the unionized state. That is, all the donor labels are occupied with electrons. As temperature increases slightly, some of the donors get ionized and contribute electrons to the conduction band. Also, some of the electrons from the valence band will jump to the conduction band, and it will leave behind some holes in the valence band. The number of holes produced in this process is very small. Therefore, the Fermi level in the n-type semiconductor EF must lie somewhere near the middle of the donor label and the bottom of the conduction band, that is EC. Similarly, in p-type of semiconductor, the acceptor level EA will lie below the intrinsic Fermi level, and the actual Fermi level for the p-type semiconductor, that is EF, will lie in between EA energy level and EV energy level. But at sufficiently high temperature like room temperature, the donors or the acceptors will get completely ionized. So that is complete ionization. So for n-type semiconductor, the impurity type is donor of electrons. At sufficiently high temperature, all the donors will be ionized. So for the case of complete ionization, the concentration of donor atoms is given by Nd equals to Nc times exponential of minus Ec minus Ef divided by kBt, where Nc is 2 times 2 pi Mn star kBt by h square whole to the power 3 by 2. Here Nc is known as effective density of states of electrons at the conduction band edge, that is at energy level Ec. If we just take the logarithm on both sides and after some rearrangement, we will get the Fermi level of n-type semiconductor as Ec plus kBt times ln of Nd by Nc. Now at a particular temperature, the Nc is constant, so the EF energy level will depend on only the donor concentration, that is Nd. As Nd increases, the EF energy level of the n-type semiconductor will increase. In the previous slide, we have already seen the Fermi level of the n-type semiconductor will depend on the concentration of donor atoms doped in that semiconductor. Now, according to the question, we will consider two cases. In the first semiconductor, the donor concentration is Nd and the Fermi level is at EF1. And in the second semiconductor, n-type semiconductor, the concentration of donor is 100 times Nd and the Fermi level will lie at EF2. As the donor concentration in the second type semiconductor is greater than the first semiconductor, so obviously the EF2 will be greater than EF1. So we have to basically calculate this difference, that is EF2 minus EF1, which is difference of the Fermi level of these two semiconductors. Also, some informations are given. We have to consider the situation at temperature 300 Kelvin and the thermal energy is given by 25 millielectron volt. Now, we will directly use the formula for Fermi level in n-type semiconductor for both the cases. In case 1, the Fermi level EF1 is equal to Ec plus kBt times ln of Nd1 by Nc, while Nd1 is the donor concentration in the first n-type semiconductor. For the second n-type semiconductor, where the doping concentration is increased by 100 times, the Fermi level EF2 is Ec plus kBt times ln of Nd2 by Nc. Here Nd2 is 100 times of Nd1. So the shift in Fermi level due to the increase in doping concentration by 100 times, the del EF is given by EF2 minus EF1, which is kBt times ln of Nd2 by Nc minus ln of Nd1 by Nc. So del EF equals to kBt times ln of Nd2 by Nd1. Now Nd2 is 100 times of Nd1, so kBt will be ln of 100 Nd divided by Nd. So Nd will cancel out from the numerator and denominator, so del EF will be kBt times ln of 100. Now at temperature 300 Kelvin, the kVt, that is thermal energy value, is 25 millielectron volt. So if we put that kVt value, we'll get del EF 25 times ln of 100 millielectron volt. So our del EF will be around 115 millielectron volt, and this is the final answer for this question. According to our solution, the shift in the Fermi level in millielectron volt at 300 Kelvin is 115 in the integer form. So this question was asked in the GATE Physics paper 2021. This is a 2 marks MCQ type question, and this question was asked from the topic solid state physics, specifically from the chapter Semiconductor physics. In the question it is given that in a semiconductor the ratio of the effective mass of hole to electron is 2:11 and the ratio of average relaxation time for hole to electron is 1:2. The ratio of the mobility of the hole to electron is option A 4:9, option B 4:11, option C 9:4 and option D is 11:4. So in order to solve this problem, we have to directly use the expression for mobility derived from the root theory of electron gas model. Now we know in a semiconductor there are two types of charge carriers. One is holes and other is electrons. Now holes are responsible for the conduction or the transport in the valence band, and electrons are responsible for the conduction or transport in the conduction band. So we will apply the formula for mobility for both the electron and holes, and we will take the ratio to find our desired answer. So let us go to the solution part. Now from the root theory of free electron gas model, we know the mobility of a charge carrier is given by mu equals to mod of E multiplied with tau divided by m star, where E is the electronic charge, which is basically 1.6 into 10 to the power minus 19 coulomb. Tau is average relaxation time for the charged particle. It is also known as the mean scattering time, and m star is basically the effective mass of charged particle. Now the effective mass of a charged particle is defined from its actual mass. The effective mass is a quantity that is used to simplify band structure by modeling the behavior of a free particle with that mass. Now in the question it is given that the ratio of the scattering time for hole to electron is given by 1:2 and the effective mass ratio for the electron and hole is 11:2. We have to find the ratio of the mobility for holes to electron. So we will take the ratio of the mobilities for holes to electron. So after taking the ratio, we will get mu hole by mu electron equals to tau hole by tau electron multiplied with m star electron by m star hole. Now in the question it is given tau hole by tau electron is 1/2 and m star electron by m star hole is 11/2. So ultimately multiplying this we will get 11/4. So our result for mu hole is to mu electron is 11:4. So among the four options, the option D, that is 11:4, is the correct answer for our question. This question was asked in the GATE Physics paper 2021. This is a MCQ type question having 2 marks, and this question was asked from the topic solid state physics. Specifically, the chapter of the question is magnetic properties of material. The question is the free energy of a ferromagnet is given by F equals to F naught plus A naught times T minus Tc times m square plus B m to the power 4, where F naught, A naught and B are positive constants. M is the magnetization, and T is the temperature of the ferromagnet, and Tc is the Curie temperature. So that is the phase transition temperature from ferromagnetic state to paramagnetic state. The relation between m square and T is best depicted by, so there are 4 plots of m square versus T are given. So we have to choose the correct one, which is basically depicting the relation between m square and temperature T. So let us see how to get the correct answer for this question. The Helmholtz free energy dF for a system is given by less or equals to minus P dV minus S dt. Here P is the pressure, V is the volume, S is the entropy, and T is the temperature. For a process in which the temperature and the volume remains constant, the Helmholtz free energy F will be minimized. In another way, we can say that during the phase transition, which is spontaneous process, the F will be minimized. So we have the condition that is del F del M equals to 0. Here M is the magnetization for a magnetic material. So according to the question, we have the free energy of the ferromagnetic system is given by F equals to F naught plus A naught times T minus Tc times M square plus B times n to the power 4. Here F naught, A naught and B are positive constants. M is the magnetization of the ferromagnet, T is the temperature of the ferromagnetic system, and Tc is the Curie temperature of the ferromagnet, that is the temperature of phase transition. Now we have to minimize this free energy of this ferromagnet. So we'll have del M of F naught plus A naught times T minus Tc times M square plus B m to the power 4 equals to 0. So this will give 2 times m A naught times T minus Tc plus 4 times m cube times B equals to 0. So we'll take 2m as common, then we will have 2m times A naught times T minus Tc plus 2 times m square B equals to 0. So from the last equation we have two conditions. First one is 2m equals to 0. And second one is A naught times T minus Tc plus 2bm square equals to 0. Now this first relation is not true, because for a ferromagnetic system it is magnetized, so m cannot be 0. So we will not consider this. So we will consider this second expression. So this is A naught times T minus Tc plus 2bm square equal to 0. This will give 2bm square equals to A naught times Tc minus T. From here we can get the m square, that is A naught Tc divided by 2b minus A naught by 2b times T. So this is a expression of a straight line. If we consider this m square equals to y and T as x, so if we plot this straight line equation, then it will give the m square versus T plot like this, which has an intercept along the y-axis, that is the m square axis, is A naught Tc by 2b, and along the x-axis or t-axis it has the intercept at t equals to Tc. So from the 4 plots our option B is correct. So we have thoroughly discussed the solution for this question, and we found that the relation between the m square, that is magnetization square, and temperature T of this ferromagnet is best depicted by the option B, that is the m square versus T plot, which is showing linear dependence. This question is from the GATE Physics paper 2021. This is a MCQ type question of 2 marks. The topic of the question is solid state physics. Specifically, this question was asked from the chapter Magnetic Properties of Material. According to the question, as shown in the figure, inverse magnetic susceptibility, that is 1 by chi, is plotted as a function of temperature T for 3 different materials in paramagnetic states. So this plot for 1 by chi versus T is given for 3 different kind of magnetic materials. So this is the plot for the first material, this second plot is for the second material, and third plot is for the third material. So there are mainly 3 types of magnetic materials. They are paramagnetic, ferromagnetic and antiferromagnetic. So we have to identify which plot corresponds to which material. So here some informations are given. Curie temperature for ferromagnetic material is Tc, Néel temperature for antiferromagnetic material is Tn. Then we have to choose the correct statement from the following. Option A is material 1 is antiferromagnetic for T less than Néel temperature Tn, 2 is paramagnetic and 3 is ferromagnetic for T less than Curie temperature, that is Tc. Option B is material 1 is paramagnetic, material 2 is antiferromagnetic at T less than Tn, and material 3 is ferromagnetic for T less than Tc. Option C is material 1 is ferromagnetic for T less than Tc, material 2 is antiferromagnetic for T less than Tn, and material 3 is paramagnetic. And the last option, option D, is material 1 is ferromagnetic for T less than Tc, material 2 is paramagnetic, and material 3 is antiferromagnetic for T less than Tn. So we have to identify properly which material corresponds to which curve. So let us see how to solve this problem. For paramagnetic materials, from the quantum theory of paramagnetism, we know the paramagnetic susceptibility chi para is given by mu naught times n times mu effective whole square divided by 3 kVt. Here mu naught is the magnetic permeability in vacuum, n is the number density of the atoms in the system, mu effective is the magnetic moment per atom, and Kb is the Boltzmann constant, and T is the temperature of the system. So basically the susceptibility of the paramagnetic material is proportional to 1 by T. So it is inversely proportional to temperature. So at a particular temperature, all the terms except from the temperature T will be constant. So we can represent this chi para as A by T, where A is the constant. So 1 by chi para will be 1 by A times T. So it is proportional to temperature. So if we just plot this 1 by chi para versus temperature, then we'll get a straight line and that will intersect at the origin. So our second material is the paramagnetic material from our question. Now for the ferromagnetic materials, we know the susceptibility of the ferromagnetic material is given by Curie-Weiss law for T greater than Tc, that is in the paramagnetic state. So the chi ferro equals to B by T minus Tc. B is the constant here, so 1 by chi ferro will be 1 by B times T minus Tc. So 1 by chi ferro is proportional to T minus Tc. So for a ferromagnetic material, the chi ferro is proportional to 1 by T minus Tc for T greater than Tc, that is in the paramagnetic state. So if we plot the chi versus T for a ferromagnetic material at T greater than Tc, then the curve will look like this. Now we'll plot the 1 by chi ferro versus temperature. So 1 by chi ferro is proportional to T minus Tc, so it will be a straight line and it will intersect the 1 by chi ferro axis at a negative value, that is minus 1 by B times Tc, and this curve will intersect the T axis at the Curie temperature, that is Tc. So it looks like the curve for third material according to the question. So the third material will be the ferromagnetic material. Then for antiferromagnetic material, the susceptibility for antiferrometric material is given by C by T plus Tn. Here C is the constant and Tn is known as Nil temperature. So it is a phase transition temperature. So basically for temperature less than Tn, the material will be in the antiferromagnetic state, but for T greater than Tn, it will have a phase transition and it will go into the paramagnetic state. For the antiferrometric material, 1 by the antiferrometric susceptibility is given by T plus Tn divided by a constant C, and it is applicable for temperature greater than nil temperature Tn. So our 1 by chi n T is proportional to T plus Tn. So if we plot this for T greater than Tn, then it will be a straight line, and if we extend this straight line by this dotted version, then this will intersect the t-axis at minus Tn, and it will intersect the 1 by chi n t axis at a positive value. So it seems that our first material is antiferromagnetic. Now we have plotted the 1 by susceptibility versus temperature for all the three materials. Those are paramagnetic, antiferromagnetic and ferromagnetic. So this plot shows the all three curves. So from here we can conclude the graph 1 or the curve 1 corresponds to the antiferromagnetic material for T less than Tn, and the graph 2 corresponds to the paramagnetic material, and the graph 3 it corresponds to the ferromagnetic material for T less than Tc. So according to the options, our option A is the correct answer for our question. So from the solution of this question, we found that the option A is correct for this question, which means this plot 1 or curve 1 corresponds to antiferromagnetic for T less than Tn, and this curve 2 is basically for paramagnetic material, and this curve 3 corresponds to ferromagnetic at T less than Tc. This question is from the GATE Physics paper 2021. This is a numerical answer type, that is NAT, having 2 marks. The topic of the question is solid state physics. Specifically, this question is from the chapter Magnetic Properties of Material. The question is, consider an atomic gas with number density n equals to 10 to the power 20 per meter cube in the ground state of the atom at temperature 300 Kelvin. The valence electronic configuration of atoms is F7. So this means the last partially filled orbital is F, and that orbital, F orbital, contains 7 electrons. The paramagnetic susceptibility of the gas chi equals to m times 10 to the power minus 11. The value of m rounded off to 2 decimal places is, so basically we have to find the value of m which should be rounded off to 2 decimal places. There are some important informations are given which is required to solve this problem. The informations are: magnetic permeability of free space mu naught equals to 4 pi times 10 to the power minus 7 Henry per meter. The Bohr magneton mu b value is 9.274 times 10 to the power minus 24 ampere meter square. So basically the Bohr magneton is the magnetic moment of the elementary charge, that is electron, which occurs due to the spin or orbital angular momentum of that electron. And Boltzmann constant Kb equals to 1.3807 times 10 to the power minus 23 joule per Kelvin. So these informations we have to use to solve this question. So let us see how to solve this problem. According to the quantum theory of paramagnetism, we have the paramagnetic susceptibility chi equals to mu naught times n times mu j square by 3 kBt. Here mu naught is the magnetic permeability of free space. Kb is the Boltzmann constant. N is the number density of atoms. Mu j is the effective magnetic moment of atoms. Here, mu j can be written as Gj times root over j times j plus 1 times mu b, where Gj is the Landis G factor. J is given by L plus S, which is total angular momentum of the atom. And in our question, some informations are given already. N, that is the number density of atoms, is 10 to the power 20 per meter cube. Temperature of the system T equals to 300 Kelvin. The valence electronic configuration of the atoms is F7. According to our question, the atomic system has the valence electronic state F7. Now we'll see how can we accommodate the 7 electrons in the F subshell or F orbital. For F orbital or the F subshell, we know the L value, that is the orbital angular quantum number or the azimuthal quantum number, L equals to 3. For L equals to 3, we know we can have ml values from plus 3 to minus 3. So we'll have 7 ml values. So basically there are 7 electronic states in the F subshell or the F orbital. So for the 7 electronic states, we can accommodate the 7 electrons in such a way each electronic state will contain one single electron. So as you can see from this configuration of the F orbital, the ml equals to plus 3 will contain one upspin electron, and correspondingly all the other electronic states will contain a single electron with upspin. So for this configuration of the electrons in the F orbital, we will have total spin quantum number S equals to summation over all ms, that is the spin quantum number of the electron. That will be 7 times 1 by 2, that is 7 by 2. But total orbital quantum number L equals to summation over all magnetic quantum number ml. So as this is half field, so the summation of all ml will be 0 here. Now total angular momentum quantum number J equals to L plus S. So here S value is 7 by 2 and L value is 0 for this system. So this summation will give J equals to 7 by 2. So for the atomic system or atomic gas, the total angular quantum number J equals to 7 by 2. Now the spectroscopic term for the atoms with valence electronic configuration F7 is given by 8s 7 by 2. This spectroscopic term is generally represented in the form of 2s plus 1 Lj. In our case, the S value is 7 by 2. So this 2s plus 1 will give 8. Now the L value, that is the total orbital angular quantum number, L equals to 0. For this we are having here x, and the total angular momentum quantum number is 7 by 2, that is J equals to 7 by 2. So we'll have here 7 by 2. Now the Landis factor is defined as Gj equals to 1 plus J into J plus 1 plus S times S plus 1 minus L times L plus 1 divided by 2J multiplied with J plus 1. So we have for our system S equals to 7 by 2, L equals to 0 and J equals to 7 by 2. So we'll put this S value, L value and J value in this formula of the Landis factor. So we'll have the Landis factor Gj equals to 1 plus 7 by 2 times 7 by 2 plus 1 plus 7 by 2 times 7 by 2 plus 1 minus 0, as here L equals to 0, divided by 2j times j plus 1. Here j equals to 7 by 2. So we will have here in the denominator 2 times 7 by 2 times 7 by 2 plus 1. Now if we calculate this, we will get the Lagrange factor for our system Gj equals to 2. Now we will calculate the effective magnetic moment per atom. The effective magnetic moment per atom is given by mu j, which is given by this formula, that is mu j equals to Gj times root over j times j plus 1 times mu b. Here Gj is the Lagrange factor of the atom, J is the total angular momentum quantum number of the system, mu b is the Bohr magneton. We have already calculated the Gj and J value for our system. The Lagrange factor Gj is 2 as per our calculation, and J value is the 7 by 2. So we'll put the values here. So we'll get 2 times root over 7 by 2 times 7 by 2 plus 1 and mu b. Now mu b is given already in the question, that is 9.274 times 10 to the power minus 24 amps meter square. So if we calculate this, then we will get mu j equals to root over 63 for this two term, 2 times root over 7 by 2 times 7 by 2 plus 1 times mu b. So mu b will put the value. So we'll get root over 63 times 9.274 times 10 to the power minus 24 amps meter square. Now the paramagnetic susceptibility from the quantum theory is given by chi para equals to mu naught in mu j square divided by 3 kBt. So we have already calculated the mu j value, it is given here, and from the question we know mu naught value, in value, and the temperature of the system is 300 Kelvin, and Kb is the Boltzmann constant that we already know from the question. So we'll put all the values here, then we will get chi para equals to 4 pi times 10 to the power minus 7, that is the mu naught value. In value is 10 to the power 20, and mu j squared is the this root over 63 times 9.274 times 10 to the power minus 24 whole square divided by 3 kb. K value is 1.3807 times 10 to the power minus 23 times temperature value of the system, that is 300 Kelvin. So after putting this, if we calculate this, we will get chi para equals to approximately 5.48 times 10 to the power minus 11. So we have to find the value of m, which is actually here 5.48. So the value of the m as it has been asked in the question, that is 5.48. So we have already solved this problem in details, and we found that the value of m in the paramagnetic susceptibility of the gas chi equals to m times 10 to the minus 11 is 5.48, which is rounded off to 2 decimal places.